This slide shows some common expression for BigO time complexity in their ascending order of time growth. That is, the curve are in the left hand side are showing how the time taken or the execution time of an algorithm is growing with the number of data item. And from top to bottom in this list, that is showing the ascending order of that growth. So the first one is order of 1, which shows the minimum time growth, or you can say order of 1 means it does not grow with the time at all. That means even if you grow your data items from 1 to 100 to 1000 to 1 million, whatever way you grow your data item, your algorithm will take the constant amount of time, and that is notified by this curve, and it is called order of 1. The next thing is order of log n, which is depicted using this curve. So order of log n shows some growth with data item, but it is very slow growth. Means you can increase the data item from 1 to 10 to 100 to 1000 to 1 million, and the time will also grow with this data item, but the growth is very slow. So these things are, and as if the growth is slow, that is the desirable property of an algorithm. So if you can, for a problem, if you can design an order of 1 algorithm or order of log n algorithm, that's very desirable property for the algorithm, because the time is not growing, or if growing, they're growing very slowly. Well, the next one is order of n, which is depicted using this curve, where the time taken is growing almost proportionally with the number of data items. So this is depicted as order of n. The next worst time growth, or you can say the next larger time growth, is order of n log n, which is depicted by this curve. So order of n log n, because of this log n is multiplied with this n, that is why it is showing larger time growth over the increase in number of data items compared to order of n. So order of log n is growing very slowly, order of n is growing faster than that, and as you can see in here, order of n times log n is actually growing even faster than order of n. The next one is order of n square, which is depicted using this curve. Here the time growth is much more faster compared to this order of n log n. So, and here, until this point, if your algorithm takes order of n square or n cube or n raised to the power 4 or n raised to the power any constant number, then we call that algorithm as polynomial time algorithm. So that is, the time growth is in some form of polynomial of n, that is n raised to the power some terminal, some number, some constant number, 2 3 4, something like that. So until you can design an algorithm for a problem which is taking polynomial time, That means you can solve the problem computationally and still it is an acceptable solution for the problem. But whenever it comes like this, when it comes to when n goes, that is the number of data items goes as the exponent to the time complexity term, that is 2 raised to the power n or 3 raised to the power n or 4 raised to the power n, or in the way like n raised to the power n. Whenever n goes as exponent, then the algorithm is considered as computationally not feasible at all. Why? Because for a large number of data items, the process will not end at all. The execution time growth is so fast with number of data items in these cases, this process will not end when the data item will grow, number of data items will grow appreciably. So here is the thing. Let's say you are given a problem and you have like multiple different way to solve it. So you designed an algorithm with order of 1 growth, that is no growth at all. Then you designed another algorithm with order of log n, another algorithm with order of n, another algorithm which takes order of n log n, another with order of n square, and another with order of 2 raised to the power n. So which one will you select? Of course, which one is showing no growth over the data item, that is order of 1. So given multiple algorithms for same problem, you should select the algorithm in this order, this from this top to this bottom. So this one is the best algorithm for solving that problem, and this one is the worst algorithm to solve the problem. Well, now one more thing I would like to clarify here, that is, you should not judge an algorithm by the time taken for very small amount of data item. What I am trying to say is, consider this order of 1 curve and this order of n curve. So if you, let's say, when you are taking only one data item, as you can see in this curve, it may happen that order of n is taking less time compared to your order of 1 algorithm. Not only one, let's say for 10 data items also, it may take less time, that is order of n is taking less time than order of 1, as you can see in this curve. But that does not mean order of n is better than order of 1. Why? Because at some threshold point, let's say this, which is, let's say, 100 data points, after some threshold data point, order of n algorithm will start taking more time compared to this order of n, and as the data number as the number of data item will grow, the algorithm will show more and more time differences. So do not judge an algorithm by with a very small amount of, or consider a small number of data items, the time taken for a small number of data items. Rather, you have to think always from the larger number of data items and how the time is growing over that.